this idea of a Mackey functor, and there's an idea of a Tambara functor. And these are supposed to generalize abelian groups and commutative rings, and in sort of an equivariant direction. So what I mean is, for any finite group G, or really any group G, I can make a notion of like a G Mackey functor or a G Tambara functor. And in the special case that G is the trivial group, these notions reduce to just having an abelian group or a commutative ring. It's a generalization in that sort of sense. So if G is the trivial group, I recover these classical notions. But if G is some other non-trivial group, I get some sort of fancy, new, weird, bizarre algebraic gadget. So I'm going to start by trying to tell you about what these algebraic gadgets are. And then I'll tell you what I've been working on, which is generalizing these notions, not just having this sort of like equivariant generalization, being able to somehow go beyond that, talk about Mackey functors and Tambara functors that appear in non-equivariant contexts. So I'll have to explain what the heck I mean by that. And the main thrust, the point of doing this kind of stuff, this sort of generalization, is to take the theorems that we have about G Mackey functors and G Tambara functors, which are useful in equivariant homotopy theory, generalize them to more bizarre contexts, and then apply them in new special cases. So we'll talk a little bit about motivic homotopy theory and how Mackey and Tambara functors show up there. All right, but let me get started just by trying to tell you about these things, the Mackey and Tambara functors for a finite group G. And let's start with Tambara functors, because I think that'll, they're a little more complicated, so if I can explain those, we can also get Mackey functors, no problem. And to figure out Tambara functors, let me actually start over here, all the way at the beginning with commutative rings. I'm going to try to tell you what is a commutative ring, but in a very strange way. Okay, so if I have a commutative ring, I get automatically a way to interpret polynomial expressions as functions. So let me give you an example. Let me write down a polynomial expression, x squared plus y squared. That's some kind of polynomial. If I have a commutative ring, this if R is a commutative ring, suddenly I can interpret this expression, this like purely syntactic thing, as an actual function from R squared to R, where I take two inputs, x and y, and I produce one output, x squared plus y squared. That's something I can do. All right. And okay, so in this sense, anytime I have a commutative ring, I get a way to interpret polynomial expressions. And the perspective we're going to take on commutative rings is to sort of work backwards from here. We're going to see commutative rings as, we're going to have the perspective that a commutative ring is a thing that can interpret polynomial expressions. That's what a commutative ring is going to be. So let me try to give this like weird alternate definition of commutative ring. And to do that, I'm going to have to tell you what are polynomial expressions. So let me do that in also a strange way. So when I have a polynomial expression like this, or actually let me take a different example. Let me take some kind of tuple of polynomials like xy, x squared plus 2y. Okay, here's a tuple of two polynomial expressions. I'm going to interpret this collection of polynomials as some diagram in the category of finite sets. And so the way that's going to work is I'm going to have a finite set here with two objects called x and y. And then I'm going to look at my polynomial expression and I'm going to say, how did this get built up from x and y? Well, first of all, I had a copy of x here. I had two copies of x here, and I had two copies of y here. But overall, I only needed 3 copies of x in total to make this collection of polynomials. So I'll put 3 dots here. And overall, I needed also 3 copies of y to make this expression. Okay. And I'm going to just draw some arrows here to indicate that these 3 dots are copies of x, and the other 3 dots are copies of y. Okay. So I have 3 copies of x and 3 copies of y. And the next thing I do when I want to make this polynomial xy, or x squared plus 2y, is I have to multiply some of these things together. I have 3 copies of x, but I need 2 of them to be multiplied together over here, and I need 1 of them to be multiplied by a y over here. So let me do that. I'm going to notice I actually have 1, 2, 3 different monomial terms over here. So let me draw 3 dots for those. The first monomial term has an x times a y, so I'll draw that like this. The second monomial term has 2 x's multiplied together. And the third monomial term, actually, is a bit of a lie. This 2y I'm really going to interpret as y plus y. So that's going to be two separate monomial terms, each of which only has a single y in it. Okay. And then finally, I have my like xy, my x squared, and my y, and I need to add some of these things together. I need the xy actually all by itself. But then in my other polynomial expression, I have x squared plus 2y. I have the x squared added to the two copies of y, all combining to make a single guy. Okay, and so what I've just drawn, these like dots with arrows between them, is some diagram in the category of finite sets. I have a finite set with 2 elements, a finite set with 6 elements, a finite set with 4 elements, and then a finite set with 2 elements. And overall, this diagram encodes this pair of polynomials, xy comma x squared plus 2y. I guess to be more precise, I should really give these outputs some names. So let me say this like, this output is called A and this output is called B. Then really this diagram is encoding some kind of assignment, A equals xy, B equals x squared plus 2y, where the inputs and outputs are both labeled. But the names of the elements in the sets in the middle don't really matter. I mean, what was this element in particular had no meaning at all. It was just some sort of like bookkeeping object. So the inputs and outputs being labeled is important, so I know which input is which and which inputs are being combined with other inputs and what's the order on the outputs and all that sort of thing. These labels have meaning, but the elements in the middle, their names don't matter. All right, but at least I just want to communicate for now that when I have a tuple of polynomials like this, in this case I had 2 polynomials or whatever it is, I could try to encode it via some diagram in the category of finite sets. But in order to make this work, I guess the polynomials are going to need to have natural number coefficients. So those could be 0, I guess, but that's sort of like not having a term at all. If I had negative coefficients, I wouldn't have a good way to express that in this diagram here, right? This only allowed me to sort of combine things together, not produce virtual things. And I need, I guess, finitely many polynomials. So a finite, maybe indexed collection of polynomials with natural number coefficients. And really, that's all there is to it. As long as I have a finite index collection of polynomials with natural number coefficients in finitely many variables.
Hey, Ben, can I ask a question?
Yeah. Please do, yeah.
Yeah, how is this related? So another way you could think about a commutative ring is as some kind of product-preserving functor from the category of finitely generated polynomial algebras with coefficients in the integers. How is this perspective related to that?
Yeah, I'm actually about to state that. It's an excellent question.
Okay.
So yeah, so we're going to use these diagrams as the morphisms in a category. And in that category, the product, or there's going to be a categorical product, and the product preserving functors from this category are going to be almost exactly commutative rings. They're really going to be commutative semi-rings because we didn't have subtraction. Yeah, so that's, you read my mind there. Okay, and so these sorts of diagrams correspond really bijectively to this sort of data. A finite index collection of polynomials and finitely many variables with natural number coefficients. Those can all be sort of uniquely encoded in these diagrams. Although, like I said, the labels on the inside don't matter. So in other words, the specific value of this set here and this set here wasn't really important. It was more just the combinatorics of how many things were mapping to this point, how many things were mapping to that point, how did those things get combined? So let me say that a little more formally. I'm going to define a category called P subset. It's the quote unquote polynomial category, where the objects are finite sets. And the morphisms from a finite set X to a finite set Y are isomorphism classes of diagrams, which I'll draw like this. So maybe I'll put an A, and a B, and a Y here. So this diagram lives in the category of finite sets. A is a finite set, B is a finite set. These are functions between the sets. And 2 of these diagrams are going to be isomorphic. So maybe I have another one here, an A prime and a B prime. These diagrams are going to be isomorphic if I can find isomorphisms here that make the diagram commute. So I'm not allowed to mess with X or Y. These labels here were important. Those had meaning. but the labels on the inside did not matter. Those could be changed freely. Okay, so I've told you the objects and I've told you the morphisms. I need to tell you how to compose morphisms in this category. So how are we going to compose two morphisms if I have this sort of like a diagram from X to Y encoding a finite collection of polynomials, and then a diagram from Y to Z encoding a finite collection of polynomials? How do I compose those two things? The answer is it's complicated, but we know there is something that's going on. I mean, if I write down the polynomials and I tell you, please compose these polynomials for me, I'm sure everyone could do it, right? We all know how to compose polynomials. So there's some composition operation that works here. It's just not clear exactly how to write it down in terms of the diagrams. It gets a little complicated, but there clearly is some way to do it. You can always compose polynomials. We know how to do that. Okay, so that's something we can do. And I'll come back to this in a sec. How do we actually define the composition in terms of diagrams? But hopefully you can believe that this really is a category. There's an identity morphism for every object, which encodes the polynomial that takes like XYZ maps to XYZ. That's a collection of three polynomial expressions that represent sort of the identity morphism on three inputs. And so there's these identity morphisms. We have composition. The composition is associative because it's just implementing composition of polynomials. It's a real category. Okay. And it's essentially small because we took classes of diagrams up to isomorphism, and there's only a set's worth of finite sets. So it's a nice, pretty compact little guy. And there's another nice thing about this category, which is maybe, let me just say fact, related to the comment from earlier, which is that in this category P subset, the product is given by disjoint union. So let me explain what I mean by that. What I mean is, if I have, let's say, some morphism in P subset from a set like XY to a set like ABC, disjoint union DE, what does this look like? This looks like some list of polynomial assignments. A equals blah, 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 B equals blah, 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 C equals blah, 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 D equals blah, 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 E equals blah, blah, blah. But if I have all this data, giving all this data for this set of outputs is the same as giving assignments for A, B, and C, and then giving assignments for D and E. So this is the same as having two morphisms, one from XY to ABC, and one from XY to DE. So this is the way in which taking the disjoint union of two finite sets actually implements the product in this category. Mapping to a disjoint union is the same as mapping to the two components. Okay, and so now let's make good on our promise to actually explain what is a commutative ring. Given a commutative ring R, I can make a functor R underline from P subset to sets, uppercase set for all sets not necessarily finite. And what this functor does, if I give it some finite set, just gives me that power of X or functions from N to R, or N tuples of elements of R, however you want to think about it. And if I have a morphism from N to M, that represents having M many polynomials in these inputs, and I can interpret that as a function from R to the N to R to the M, some actual function. And what I mean by interpret that is exactly the sense I said earlier. I'm going to scroll up a little bit to hopefully recover that. When I have some polynomial expression like this, I can interpret it as a function from R squared to R for any commutative ring R that I have. And if I had a tuple of polynomials, I could interpret, if I had X squared plus Y squared and also XY, I could go from R squared to R squared, have the two outputs. So every time I have a finite set, every time I have a sort of like this polynomial data between two finite sets, one of these diagrams, I can interpret it as a function between Cartesian powers of my commutative ring. Okay, but I actually didn't need the full structure of a commutative ring. I was only allowing natural number coefficients. And so really any commutative semi-ring would be able to interpret polynomials in this way. Okay, let me pause real quick here. Questions about this setup? It's all feeling good and clear. Okay. All right, but please feel free at any time to interrupt me. All right, so if I have a commutative semiring, I get a functor like this from P subset to set. And what's more, this functor is product preserving. And this is the connection to the Levier theory comment from earlier. What I mean is that if I take R underline of a disjoint union of two finite sets, say n1 and n2, I get R to the power n1 disjoint union n2, which is the same as R to the n1 cross R to the n2. Okay. It sends products in the category P to products in the category of sets. All right. So that's true. And because there's a little more to product preserving than just that there exists an isomorphism. It's a particular isomorphism. Okay. But now here's a claim. And this is, I guess, probably due to Levier. The category of commutative rings is actually isomorphic, or let me just say equivalent, to the category of product preserving functors from P set to set. Given any commutative ring, I produce one of these product preserving functors. But actually, these are the only product preserving functors you can ever have. Every product preserving functor from P set to set really just encodes the data of a particular commutative ring. And the reason is, okay, so I have this functor that takes R to R underline. And let's say I had some functor here, some product preserving functor from P set to set. Then I can figure out what the underlying ring should be by evaluating this on a 1-point set. That should give me like R underline of a 1-point set should just give me R. That gives me the underlying set. And then how do I get the binary operations of addition and multiplication? If I have f of 1 squared, because f is product preserving, that's the same as f of 1 disjoint union 1. And then I have these maps from 1 disjoint union 1 to 1 in the polynomial category, which I'll call plus and times. In the polynomial category, if I have a set with 2 elements and a set with 1 element, I can make a polynomial expression that has 2 inputs and 1 output. For example, x comma y goes to x plus y, or x comma y goes to x times y. These are morphisms in the polynomial category, which my functor has to interpret as actual functions in set. And the product preserving condition tells me that those interpretations are going to be actual binary operations on f of 1. And then you can check the axioms. I mean, the composition in this polynomial category somehow is set up to make polynomials compose in the way they do, where multiplication distributes over addition and so on. And so the axioms of commutative rings are actually encoded in the category P subset. All right. So
excuse me.
These are, oh, sorry.
How do you cover subtraction?
Sorry. That's a good point. We don't. And so this was a lie. It's commutative semirings.
Okay.
Thank you. Thank you. These are really commutative semirings, or some people would say commutative rigs. They're rings, but you don't necessarily have subtraction, not necessarily additive inverses. Thanks very much. Yeah.
Sure.
Okay, and so that's commutative semirings. And then we can recover commutative rings inside commutative semirings, as these are like the product preserving functors where each of the addition operations that I get, where the addition operation that I get has inverses. That's some condition you could impose on a commutative semiring to recover the category of commutative rings. Oh yeah, thank you. All right, so that's the story about commutative rings. And I'm supposed to tell you about Tambara functors. So let me move on to that.
Before you do, can I ask a question about the last remark you made?
Yeah, please do.
How exactly, like, so, okay, if I want to produce a, like, you know, additive inverse to y, say, like, I fix the digit y in x plus y and look for an inverse to that function, how does that translate into this like diagrammatic language? Or am I running, this is complicated because composition is complicated?
Yeah, it's a bit complicated. So writing it down diagrammatically, like I want there to exist inverses, is a little hard to do. It's hard to encode this as diagrams. And so it's better to say, I have this like diagram interpretation of commutative semirings, and then there's a condition I can impose on these functors as a property I can look for the functors to satisfy. Every time I have one of these functors, I get a binary operation called plus, and I can wonder if that binary operation on the level of sets like just has inverses. You always get a commutative semiring, and then you can just say, is it a commutative ring? And that's the way you can try to pick out commutative rings. And there does exist a Levier theory of commutative rings, but it is more complicated to describe. You have to do some, you basically want to do some group completion of this category P subset, which is canonically enriched in commutative monoids. You can do a sort of group completion Hom set wise in this category, and you get a category that's enriched in abelian groups, and then you take product preserving functors to set, and that works. Does that help answer the question?
Yeah, thank you.
Okay, cool. All right, yeah, so right, so that's commutative rings. We can identify them inside this category of product preserving functors. And we're going to do the same kind of thing for defining Tambara functors. And so I can really just tell you exactly what the definition of a Tambara functor is. What I'm going to do is take this category P subset, but instead of using the category of finite sets, I'm going to use the category of finite G sets. So take a group G and form this category P sub G set in exactly the same way that we form the category P subset. The objects are finite G sets. The morphisms are these isomorphism classes of diagrams, which I'll call bispans. So a morphism from X to Y is an isomorphism class of diagram like this in the category of finite G sets. Exactly the same condition about isomorphism. What it means for two of these diagrams to be isomorphic is that I can fill in this picture here. Okay. And then the composition, okay, again, still question marks. So in the category of finite sets, this felt easy because we had this identification of diagrams with polynomials, and we know how to compose polynomials. And so at least in theory, if you're given two diagrams to compose, you could write down the corresponding polynomials, do the composition by hand, and then write down the new diagram that's supposed to compose to. In the category of finite G sets, it's unclear exactly what to put here. But here's my claim. I'm not going to actually tell you how this composition works, but my claim is that there is a nice way to categorically describe how this composition works. We can describe this in completely categorical language. And basically the way this works is you take two of these diagrams, you look at all the morphisms involved, you form a bunch of pullbacks, you form some quote unquote exponential diagrams, you do all this like crazy category theory constructions, and somehow you produce this new bispan in the end. It's supposed to be the composite. And so I can describe this process somehow entirely in terms of category theory. And then I just take that definition and I use the same categorical definition here. I take the composition of polynomials, I try to write it down in terms of the language of category theory, and then I use that definition to define the composition in this new category, P sub G set. And somehow that's possible, but I do need some structure on my category. So what I need I said I needed pullbacks and also these quote unquote exponential diagrams. And this turns out to be exactly the data that says that the category of finite G sets is locally Cartesian closed. Okay, so what that means is if I take any slice category, G set over some object X, this slice needs to be Cartesian closed for all X. And what that means is that this slice category has all finite products that corresponds to the category of G sets itself having all finite pullbacks. And additionally, the closed condition means that the products in the slice category, the product functors have right adjoints. There's an internal Hom in the slice categories. That's the meaning of locally Cartesian closed. And so if I have this condition, which I do, the category of G-sets does have this property, then I can define this composition operation just by exactly mimicking sort of categorical definition for finite sets, whatever that happens to be. It's a little bit complicated, but hopefully you can believe me that it exists. And so I can produce this new category set called P sub G set, and now I can tell you what a Tambara functor is. G is a group. A G Tambara functor is a product preserving functor from P sub G set to sets. And so if G is the trivial group, then a finite G set is just the same as a finite set. And then this product preserving functor, like we saw before, is just a commutative semi-ring. So I haven't exactly recovered commutative rings. And so I have to add an additional condition such that when I take any of my output sets and I look at the addition operation I get on that output set, this has inverses. Okay. Again, in the category of finite G sets, I get this map called plus from in P sub G set from any object disjoint itself to itself. That's something I can just write down in the polynomial category. And then any functor from the polynomial category that preserves products will give me a binary operation on each output called plus. Okay. And so if I take G to be the trivial group, then this recovers exactly the definition of commutative rings. I have commutative semi-rings such that addition has inverses. And that's the definition of a G Tambara functor. And so let me pause there before trying to say more stuff. Questions, thoughts, feelings?
Is there a reason, is there a reason why you choose the map, like the morphism, to be bispans? Like, because I guess you can choose the arrow to come from X to A instead of from A to X, right? It's just like, you just look at like that diagrammatically. Like, for example,
so here you want to say, what if I just did this instead with the arrow pointing the other way? So the difference is that in my, when I'm trying to encode a polynomial, let me rewind a bit. Way up here, I had these two inputs, X and Y. And what I needed to do was make a bunch of copies of X and a bunch of copies of Y. And so I wanted these three things here all to be X. But I can't have a function that sends one point to three different points, right? So the arrows have to go the other way. I need to say that these 3 points are all X. What I want to say is they all map to this guy X. They're all living over X. If the arrows went the other way, it wouldn't be a function. Is that what you were asking? Maybe that was beside the point.
The objects not just diagrams, but actually the horizontal, like moving from one column to another must be a map of sets.
Yeah, sounds good.
Okay.
Could I ask,
Yeah.
Ben? I think you're doing things over Z in the sense that rings are Z algebras and so forth. And sometimes you want to do Mackey functors or what have you over some other ring, like over a field or something. How would that encoding appear in your version if you wanted to do it over?
That's a good question. So yeah, that's a very good question. I don't have a good answer for this right now. There's for Mackey functors over some field, you can write this down sort of as a condition on the Mackey functor, or rather as like an additional structure on the Mackey functor, that each output of the Mackey functor comes with a K algebra structure, or it comes with a K module structure, blah, 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 blah. And the morphisms are compatible. And I think there's probably another way to do it where you K-linearize the category before you take functors out, but I would have to think about it more. You have to additionally then impose that the free Mackey functor on one object goes to actually K. But then I think with that kind of condition, you get the right category of K-linear Mackey functors.
Well, I was imagining if it might involve something like that, but I couldn't quite see how to sort of K-linearize. But like with Mackey functors, if you've got a category with G sets and spans of G sets and so forth, then you can take functors into K modules. and that will
Yes.
get you out of trouble. And so insert the K into the target category.
Yeah, and so for Mackey functors, this works well, and for Tambara functors, it doesn't. And the obstruction here is that for Mackey functors, all the morphisms that I want to encode are actually additive. The restrictions and transfers are both additive maps. But in Tambara functors, this morphism in the middle is encoding some kind of multiplication. That's going to be a non-linear, a non-additive map between the output objects. And so I can't actually interpret a Tambara functor as a functor to, for example, commutative semirings, even though each output object is going to be a commutative semiring. The morphisms that I get between them, some of them are going to be multiplications, which are not ring homomorphisms, or even, linear at all.
Thanks.
I have a related question to Peter's question, which is like, what is the relationship between like a k-linearized version and then like taking something like a constant green functor or something like this, and then considering modules over it in the category of Mackey functors?
Yeah, it's a good question. I'm not totally sure. There is some relationship here. If you have a module over some constant Mackey functor with value k some field, then you should get K module structure on all of your output objects, but I'm not sure like exactly if we get an equivalence of categories here or something. Yeah. Yeah, thanks. That's a good question. Okay, but let me continue. Also, I should ask, do I have 50 minutes and then questions? Is that the plan?
55 is also good.
Okay. All right, thanks. So, all right, so we said what is a G-Tambara functor, and now let me just like make an additional generalization. So let's see the any category, which is, okay, so let me list some conditions. First of all, it needs to be locally Cartesian closed, the condition I mentioned before. That is exactly the thing we needed to interpret the composition in this category. I need, secondly, that C has finite disjoint coproducts, which says, first of all, having finite coproducts gives me the product in the category P. That's going to be the product in the polynomial category is going to be given by like disjoint union, the coproduct in the original category C. And then third, I want C to be locally essentially small. Okay, this condition is not necessary for what I'm about to say, but it will be necessary later. So I'm just going to impose it now, blanket statement, so I don't have to keep saying more conditions. So if I have these three conditions, then I'm going to say a C Tambara functor is a product preserving functor from P sub C to set, such that each output object with its addition operation is an abelian group. Just exactly the same thing, but instead of using specifically the category of finite sets or the category of finite G sets, I just take any category where I can run the exact same construction and just impose the same definition. That's the notion of a C Tambara functor. And so if C is the category of finite G sets, I recover normal Tambara functors for finite groups. In particular, if C is the category of finite sets, then I get commutative rings. But this could be any sort of more general kind of category. So important examples would be, you could take any essentially small locally Cartesian closed subcategory of a topos. Okay, so that's the sort of like G set sort of story. But then there's also examples like, here's our weird other kind of exotic example. It would be you take smooth schemes of finite type over some base, take some base scheme S, and then look at smooth schemes of finite type over S. That's it's locally essentially small. It has finite disjoint coproducts. It's locally Cartesian closed. It has all the structure that I need to make this stuff work. This is the kind of thing that you want to study in motivic homotopy theory. or rather, equivariant homotopy theory, stuff is sort of parameterized by finite G sets. And in motivic homotopy theory, stuff is sort of parameterized by smooth schemes. Okay, so I'll talk about that in a bit if we have time. But that's another context we could have. I have this generalized sort of definition. Oh yeah, sorry.
Can I interrupt for another quick question? What is X here? Is X like a terminal object like it was for sets?
Good question. X is any object. And so in the category of finite sets, yeah, I could do it for the terminal object and get the addition operation, but I could also do it for any other object. In the category of finite sets, I take any finite set n, and there's a map like this in the polynomial category that takes like x1 through xn, y1 through yn, and gives me x1 plus y1 through xn plus yn. And that's the plus operation for an arbitrary thing. And there's an analogous guy in any polynomial category. I take the map that does no multiplying of how many inputs I have, does no multiplications, and then does the fold map to add the two copies of my object together. And that encodes the addition on any object in any sort of polynomial category.
Got it, thank you.
I want to do this for, yeah, thanks. I want to do this for all objects just so that, that's the one that gives me the right notion of Tambara functor for G sets. Okay. So that's what a Tambara functor is. And I should also tell you what is a Mackey functor real quick. And so a Mackey functor is a product preserving functor from this category that I'll call A sub C to set, such that f of x comma plus is an abelian group for all x. And this category A sub C, this is the category that encodes the stuff that can be interpreted by abelian groups. Mackey functors are supposed to be this generalization of abelian groups. Instead of trying to interpret polynomials, I'm going to try to interpret things that I can get just using addition. And so another way to say this is that this is the subcategory of P sub C, where the middle maps are the identity in the bispans. So I have a bispan like this. I have all the objects inside P sub C, but it's not a full subcategory. I only have the morphisms where there's no multiplication going on. And that encodes the stuff that abelian groups can do, or rather that commutative monoids can do. And then this forces everything to be abelian groups. And so again, if you take C to be the category of finite G sets, you get the normal notion of G Mackey functors, if you're familiar with those. All right, cool. So we have our objects. And so now let me tell you the theorem. Okay. And maybe I'll call this part 2, a theorem. And so let me start with something that's true about Mackey functors in equivariant world with finite G sets. So if I have a finite group G and I have a subgroup H, these are finite groups, then I can think about the category of G Tambara functors. I can think about the category of H Tambara functors. And there's a forgetful functor from here to here. It turns out having a G Tambara structure is somehow more information than having an H Tambara structure. So there's some kind of forgetful functor or a restriction functor, whatever you want to call it. And this has a left adjoint. I can take an H Tambara functor and boost it up in sort of a free way to get a G Tambara functor. So I'll call that functor N. Okay. And it turns out this functor on the level of the category of Tambara functors can sort of be interpreted at the level of Mackey functors. So if I have a Tambara functor, I can forget the multiplicative structure and get a Mackey functor. If I have a commutative ring, I can look at the underlying abelian group, in other words. And here, if I have a commutative ring, I can look at the underlying abelian group. And it turns out there's a functor here, which I'll also call N, that makes this diagram commute. So this is a theorem. Due to Hoyer for the arbitrary inclusion of finite groups case, previously it was done for cyclic groups of prime power order by Kristen Miser. And then later there's an incomplete version by Chan. Incomplete is a technical term here. Something about Tambara functors. But this version of the theorem is due to Rolf Hoyer. And so the theorem is that there exists this guy here, something fits there. And it's sort of an interesting theorem. An analogy would be like, if I have an inclusion of commutative rings, I can think about the category of like A algebras and the category of B algebras, and I can go from one to the other by tensoring with B, extending scalars. And I can also go from A modules to B modules by tensoring with B, extending scalars like this. And interestingly, this commutes with the forgetful functor. That maybe doesn't sound interesting, but it kind of is. It's saying that somehow the underlying module structure of your extended algebra did not depend on the actual algebra structure at all. The algebra you had here, it didn't matter what the multiplicative structure was whatsoever. The underlying module only depends on the underlying module you started with. And so it's something kind of analogous here. It's telling us that we can figure out the underlying Mackey functor of our normed up guy by only thinking about what was the Mackey structure before, not having to remember any of the multiplicative structure that I started with. Okay, so it's a useful thing that can really help with computation sometimes. People do use this theorem in equivariant homotopy theory. And so let me state a result. With C as above. So that's locally Cartesian closed with finite disjoint coproducts and locally essentially small. There is a square. Sorry. C as above and I, x to y. Any morphism in C. There's a square, like so. And this will seem mysterious at first, but I'll explain what's going on in a sec. There are these forgetful functors here. There are these norm functors here. The norm functor on the Tambara level is left adjoint to restriction. And there's more stuff I could say, but let me leave it here. This commutes up to natural isomorphism. And so let me explain how this has anything to do with the previous theorem. It looks sort of vaguely the same, but previously we had some inclusion of finite groups that wasn't happening inside the category of finite G sets. And here the data is like some morphism in the category C, which is supposed to be the category of finite G sets. So let me try to explain what's going on there. In the category of finite G sets, here's a fun fact. The slice category of G sets over G mod H is isomorphic to the category of H sets. And the reason is if I have a G set living over G mod H, I have some structure map F. I can look at F inverse of the trivial coset. And that has the structure of an H set because this map is equivariant. If I act by H on something that lives above the trivial fiber, I stay above that fiber. And so this is an H set. And actually, this is an isomorphism of categories. These two categories are the same. And so when I'm thinking about G Tambara functors and H Tambara functors, instead of thinking about these as functors from P sub H set, I can think about this as functors from P sub the slice category of G sets over G mod H. And this guy is functors from the slice category G sets over G mod G, G sets over a point. And so this picture here looks like, let me translate it over here. Product preserving functors satisfying this additivity condition from P sub G set over G mod H to set. That's the category of H Tambara functors. And when I want to go to G Tambara functors via this norm map, I have to get some kind of functor here. Like so. Okay. And to do this, the functor is left conextend along dependent sum, where I is the map from G mod H to G mod G. When I have, there's a unique map from G mod H to G mod G because G mod G is just a point. And if I have something living over G mod H, I can just compose and get something living over G mod G. That's this dependent sum functor. That gives me a functor, in turns out, between the polynomial categories as well. And left conextending along that functor gives me a functor between these functor categories, which are the categories of G and H Tambara functors. So going from H Tambara functors to G Tambara functors can really be viewed as left conextending along this functor that I get induced between slice categories via post-composition with this unique map to the terminal object. So the theorem that I proved is generalizing this situation. Instead of using the category of finite G sets and thinking about the slices that give me finite H sets and finite G sets, I take any category with these conditions. So it could be this like motivic situation like we talked about earlier. And I can think about Tambara functors indexed in various slices of that LCC category. And then for any morphism from X to Y, I get these relationships between the categories of Mackey and Tambara functors over the various slices, given by the same sorts of left conextension formulas. This functor is going to be left conextend along the dependent sum along I, and this functor is left conextend along the dependent product along I. And those turn out to be well-defined things to do. Okay. That's, yeah, I guess I have 5 minutes left to say more things, but before I do that, any questions about this setup? I think I probably presented them in kind of a confusing way, so questions expected.
Can I ask, like, it's a lot to take in there, and with the groups situation, you've got a group G, and then you might have subgroups, and
yeah.
So you identify them because there's a morphism of groups from H to G, and it's a placement here. So you've got some category, and what is replacing G and H is what is replacing map from H to G simply any morphism I from X to Y. So you've got a lot of there.
Yeah, that's right. That's right. And so most directly, like the way to recover the original theorem by Hoyer here is to set C to be the category of finite G sets, and then take I to be the morphism between orbits like this from G mod H to G mod G. And then this recovers exactly the square that I put above, going from H Tambara functors to G Tambara functors and H Mackey functors to G Mackey functors. And more generally, you could use any morphism between finite G sets, but those all decompose as disjoint unions of morphisms between orbits. And there is some interesting thing there. Instead of just going from G mod H to G mod G, you could go from G mod H to G mod K, and there's something interesting to say there. But more generally, you could take, instead of the category of G sets, you could take the category of finite groupoids, for example. And in the category of finite groupoids, you can have all of your finite groups living, but also all of your G sets. Every time you have a group acting on a set, you can make a groupoid that sort of is a picture of the action. The objects are the points in the G set, and the morphisms are the group elements that act and send one element to another. And so you can get this category of finite groupoids that somehow has all the groups and all the G sets in it all at the same time. And then you can try to interpret this theorem and use all sorts of do norms along all sorts of wacky maps between groups and from groups to G sets and all this sort of crazy stuff.
I suppose what was motivating my question is that if we're dealing with G sets, so the category of G sets has an awful lot of like restrictions, has a technical meaning, but it's like all morphisms are epimorphisms in that category, and all sorts of special things happen. There are hardly any morphisms there, and the ones that are there we understand very well. And now you seem to have a generalization where, okay, C does have some constraint on it, the category, but aside from that, you've got any morphism, and you seem to be doing something for any morphism, which seems remarkable to me.
That's correct. Yeah, it is nice. And if you use the category of finite G sets, like you say, it's not like we have much more flexibility. All the morphisms are very restricted. But yeah, exactly like you said, C could be a load of different things, and then I could be literally any morphism in that category, and we get a square like this that commutes up to natural isomorphism. And so the proof is like a bunch of heavy-duty, really annoying diagram manipulation, which you're welcome to take a look at on the archive. Once that's up. But yeah, once you work through it all, it really does work for any morphism. Yeah. And so let me just say in the last couple minutes, like, what's kind of the point of this generalization? So I mentioned motivic homotopy theory earlier. And in equivariant homotopy theory, the reason these invariants are important is that when you have an equivariant spectrum, if you have a genuine G spectrum for some finite group G, if you take its homotopy groups, you don't just get abelian groups with a G action. You do get abelian groups with a G action, but you get more structure. You literally get a G Mackey functor. And this is why G Mackey functors are important in homotopy theory, is that they're the natural structure we get on our homotopy groups when we have a genuine G spectrum. And so if I take G spectra and I take homotopy groups, I get G Mackey functors. And if you take G ring spectra and you take homotopy groups, you get G Tambara functors. So that's where these invariants are really coming from. Maybe not historically, but nowadays, most of the time people are producing Mackey and Tambara functors in homotopy theory. It's because they're starting with a G spectrum or a G ring spectrum, and then they produce a G Mackey functor or a G Tambara functor as its homotopy groups. Those are the algebraic invariants we get. And likewise, in motivic homotopy theory, there's this category of effective homotopy sheaves, which give you motivic Mackey functors and motivic Tambara functors. And so it would take a little too much time for me to explain what these things are, or to say too much about what these things are. But actually, it's not too hard to explain the right-hand side. These motivic Mackey functors are exactly Mackey functors indexed by more or less the category of smooth schemes of finite type over some base. There's a little bit of some technical detail here to say, but more or less you can identify this notion of motivic Mackey functors, which show up in motivic homotopy theory as Mackey functors that are indexed by this totally different category. There's no G action left anymore. It's not that we actually have some group acting, but somehow the collection of algebraic invariants that we get a bunch of abelian groups with a bunch of maps between them. And these maps obey the same axioms that a Mackey functor for a finite group does. And so they have, so they fit into this picture of Mackey functors indexed by some other thing. And likewise, you can have normed algebras inside effective homotopy sheaves, and those give you Tambara functors indexed by smooth schemes. And so you can interpret this theorem for finite G sets, or for finite groupoids to do global homotopy theory, or in smooth schemes to get motivic stuff. And this theorem applies in all of these contexts, and you can norm along any morphism you like. And I guess the takeaway is sort of twofold. First of all, it's a new result about motivic Mackey functors and motivic Tambara functors. It's a new tool we didn't have before that we got just by taking the definitions, generalizing them, proving the theorem in this generality, and then just like plopping it down in this new context. And then also, hopefully this is sort of a proof of concept that like these invariants that we get, these motivic Mackey functors, these motivic Tambara functors, and global Mackey functors, and global Tambara functors, any of those sorts of things that you encounter, we should be able to take theorems from one of these domains, motivic homotopy theory, or equivariant homotopy theory, or global homotopy theory, or maybe biset functors in representation theory, and try to translate these facts that we know all over the place. Take the facts that we know about equivariant homotopy, generalize them, and then plop them down someplace else. All right, so that's the kind of stuff I've been working on. I should stop here, and thanks very much.
All right, thanks so much, Ben. Does anybody have any questions, comments?
Hi, so you mentioned applications to motivic homotopy theory, and in particular, like smooth schemes being locally Cartesian closed. What's the exponential type object that you're finding in there?
Yeah, so here's the way this works. So I want to say that smooth schemes over S is locally Cartesian closed. It turns out showing that something's locally Cartesian closed, so directly this just means that every slice category is Cartesian closed, and I need to produce an internal Helm on each slice category. There's an equivalent way to check this condition actually, which is that for all morphisms in your category, you get this dependent sum functor from smooth schemes sliced over A to smooth scheme sliced over B, which just takes something living over A and then composes, and now I have something living over B. That's the easy functor. Being locally Cartesian closed is equivalent to this fitting in an adjoint triple. Dependent sum, left adjoint to pullback, left adjoint to dependent product. And if you have this data for every morphism in your category, this is equivalent to every slice being locally Cartesian closed, or being Cartesian closed, sorry. And so for smooth schemes, this part's easy. That functor always exists no matter what. This part's also easy because I can do a fiber product and I still get a smooth scheme. And this part is called Weil restriction. There's this operation that takes a scheme living over A and performs, you construct a new scheme living over B. It's some functor from schemes sliced over A to schemes sliced over B. This functor is called Weil restriction, and it exists between these slices in particular because of the smoothness condition. In general, you don't have Weil restriction along any morphism in the category of schemes, but for morphisms between smooth schemes, you do. Does that help answer the question?
I think so. Thank you.
Yeah.
Are there any other questions? In that case, I have a question. So you started by telling us what this P set category was, and then like the generalization road that you took was like replacing set by other things mostly, right?
Yeah.
But you had these like weird bispan thingies, and you took iso classes of those, and it seems to me like there's another natural road to generalize this where you take like a bi-category and instead of doing this truncation for the iso classes, or you could even do maybe a weak double category if you allowed to like swap the foot of the thing. Is this explored at all?
Yeah, that's a great question. So in general in the literature, there is some work on this. Yeah, so you exactly can get a bi-category where the morphisms are the actual bispans, and then the two morphisms are these relations between the bispans. And you really, it turns out, you really want like Cartesian relations. You want the morphisms to be like this, where this is a pullback square. That's like, makes things work out better. But you can make this category, and there is some work exploring what are the Mackey two functors. What is the theory of like G Mackey two functors and G Tambara two functors? That's explored in some papers of Balmer and D'Ambrosio, I think. There's some work there. I don't actually know that much about it, but this has been thought about. And there's also been some work about pushing this all the way to the infinity level. So you start, instead of with like a one category C, start with an infinity category C, somehow with a little bit of structure, some kind of LCC condition, and then form an infinity category of bispans and look at infinity functors to stuff. That's work of Bogdan Krishtik. So there's been some work there, but I unfortunately don't know too much about it.
Okay, thanks a lot. All right, let's thank Ben again. Thanks so much, Ben. This was really great. And if you'd like to send either me or Anne your slides, we can post them on our website.
I absolutely will. Yeah, I'm sorry they are, as promised, very messy. But yeah, thanks so much for having me.